You think speed is simple? Distance divided by time, miles per hour, meters per second. You're driving 60 miles per hour down the highway. The speedometer says so. That's your speed. That's how fast you're moving. Straightforward, basic physics. But here's the problem. That speedometer is lying to you. Not in the sense of being miscalibrated or broken. It's lying in a deeper way. It's telling you that you have a speed, a single number that describes how fast you're moving. But you don't have a speed. Not really. Not in any absolute sense. Speed is not a property you possess. It's a relationship between you and something else. And once you understand this, once you see that speed is fundamentally relative and not absolute, everything about motion becomes stranger and more interesting, because there's one speed, exactly one, that's the same for everyone. And that speed is so bizarre, so contrary to intuition, that it forces us to completely rethink what space and time actually are. Start with something obvious. You're sitting in a chair reading this. Are you moving? You'd probably say no. You're stationary. You're at rest. Your speed is 0. But wait, the Earth is rotating. At the equator, the surface of the Earth is moving at about 1,000 miles per hour. So you're moving at 1,000 miles per hour. But the Earth is also orbiting the Sun. That's another 67,000 miles per hour. So you're moving at 67,000 miles per hour. But the Sun is orbiting the center of the Milky Way galaxy. That's about 500,000 miles per hour. So you're moving at 500,000 miles per hour. But the Milky Way is moving relative to other galaxies, relative to the cosmic microwave background, at about 1.3 million miles per hour. So which is it? Are you moving at 0, 1,000, 67,000, 500,000, or 1.3 million miles per hour? The answer is all of them, and none of them. Your speed depends on what you're measuring it relative to. Relative to the chair, 0. Relative to the sun, 67,000. Relative to the cosmic microwave background, 1.3 million. There's no fact of the matter about your absolute speed. There's no cosmic speedometer giving the one true value. Speed is always speed relative to something. This is the first big misconception. People think speed is an absolute quantity, a property of an object. It's not. It's a relationship between two objects. Galileo understood this in the 1600s. He called it Galilean relativity. The laws of physics are the same in all inertial reference frames, frames moving at constant velocity relative to each other. If you're on a ship moving smoothly across the ocean, you can't tell by doing physics experiments whether the ship is moving or the ocean is moving. You could argue the ship is stationary and the water is flowing past at 20 knots, or the water is stationary and the ship is moving at 20 knots. Both descriptions are equally valid. There's no experiment you can do inside the ship that tells you which is true. Motion is relative. Here's a classic example. You're on a train moving at 60 miles per hour. You walk toward the front of the train at 3 miles per hour. How fast are you moving? Relative to the train, 3 miles per hour. Relative to the ground, 63 miles per hour. Relative to another train moving alongside at 50 miles per hour, 13 miles per hour. Which is your speed? All of them, depending on the reference frame. This seems obvious. Speeds add. Velocities are vectors. They combine. Simple. But now comes the strange part. Light doesn't work this way. You're on a train moving at 60 miles per hour. You shine a flashlight forward. How fast is the light moving? Relative to the train, the speed of light, about 670 million miles per hour. Relative to the ground, also 670 million miles per hour. Not 670 million plus 60, just 670 million. The light's speed doesn't add to the train's speed. You shine the flashlight backward, behind the train. How fast is the light moving relative to the ground? Still 670 million miles per hour. Not 670 million minus 60, the same. The speed of light is constant, the same in all reference frames, regardless of the motion of the source or the observer. This is insane. It violates everything we know about how speeds combine. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the train's speed plus the ball's speed relative to the train. That's just addition. But light doesn't obey this rule. Light always moves at c, the speed of light in vacuum, 299,792,458 meters per second exactly, not approximately, exactly. By definition, the meter is now defined in terms of the speed of light. 1 meter is the distance light travels in 1 over 299,792,458 of a second. The speed of light is not just constant, it's the standard by which we define distance. Why? Why is light special? The answer comes from Maxwell's equations, formulated in the 1860s. Maxwell showed that electricity and magnetism are two aspects of the same phenomenon, electromagnetism. And electromagnetic waves, which include light, propagate at a speed determined by fundamental constants, the permittivity and permeability of free space. Maxwell calculated this speed, about 300,000 kilometers per second, the speed of light. But his equations didn't say relative to what. The equations didn't have a preferred reference frame. They just gave a speed. This was profoundly disturbing to physicists of the time. They thought there must be a medium, the luminiferous ether, through which light propagates. The speed of light would be c relative to the ether. Other observers, moving relative to the ether, would measure different speeds. So they tried to measure Earth's motion through the ether. Albert Michelson and Edward Morley did an incredibly precise experiment in 1887. They compared the speed of light in different directions as Earth moved through space. If Earth were moving through the ether, light should travel slightly faster in one direction, slightly slower in another, depending on Earth's velocity through the ether. They found nothing, no difference. The speed of light was the same in all directions, regardless of Earth's motion. They repeated the experiment at different times of year when Earth's velocity was different. Still nothing. The speed of light was constant. This was a crisis. How could light's speed be the same for all observers? It makes no sense. Einstein resolved it in 1905 with special relativity. He made two postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in vacuum is the same in all inertial reference frames. That second postulate is the key. Light always travels at c, no matter how you're moving. This is not because there's something special about light per se. It's because c is the speed of causality, the maximum speed at which information can propagate through the universe. Light happens to travel at this speed because photons are massless. But c is more fundamental than light. It's a property of spacetime itself. Now, if the speed of light is constant for all observers, something else has to give. What gives is space and time. They're not absolute, they're relative. Different observers, moving at different speeds, will disagree about distances and time intervals. This is not an optical illusion. It's not a measurement error. Space and time actually are different for different observers. Let me be specific. You're standing on the ground. A rocket ship passes by at 0.9 c, 90% the speed of light. There's a clock on the rocket ship. From your perspective, that clock is ticking slowly. Time dilation. If 1 second passes on the rocket's clock, about 2.3 seconds pass on your clock. The factor is gamma equals 1 over the square root of 1 minus v squared over c squared. At 0.9 c, gamma is approximately 2.3. From your perspective, time on the rocket is running slow. But from the rocket's perspective, it's your clock that's running slow. You're moving at 0.9 c relative to the rocket in the opposite direction. So from the rocket's perspective, your time is dilated. Both of you are right. Time is relative. Similarly, lengths contract. The rocket ship is 100 meters long in its own reference frame. But from your perspective, as it zooms past at 0.9 c, it looks shorter, about 44 meters long. Length contraction by a factor of 1 over gamma. The rocket's crew, however, doesn't notice anything wrong with their ship. To them, it's 100 meters long. But from their perspective, the distance between you and some distant star is contracted. They measure a shorter distance than you do. Again, both are right. Length is relative. This is how the universe maintains the constancy of the speed of light. If you and the rocket both measure the speed of a light beam passing by, you both get c. You disagree about the distance the light traveled. You disagree about the time it took. But distance divided by time gives c for both of you. The universe conspires, through time dilation and length contraction, to make light's speed constant for all observers. Here's another consequence. You can't exceed the speed of light. Ever. No matter how much energy you pump into an object, you can never accelerate it past c. Why? Because as an object's speed approaches c, its relativistic mass increases. The energy required to accelerate it further increases. At exactly c, for an object with any rest mass, the energy required becomes infinite. You can't get there. Only massless particles like photons can travel at c. Everything else is stuck below c. But wait, you might say, what if I'm on a rocket moving at 0.9 c and I fire another rocket forward at 0.9 c relative to me? Doesn't the second rocket move at 1.8 c relative to the ground? No. Velocities don't add that way at relativistic speeds. The formula for adding velocities is v total equals open parenthesis v1 plus v2, close parenthesis over open parenthesis 1 plus v1 v2 over c squared, close parenthesis. If you plug in v1 equals 0.9 c and v2 equals 0.9 c, you get v total equals open parenthesis 0.9 c plus 0.9 c, close parenthesis over open parenthesis 1 plus 0.81 close parenthesis, approximately 0.994 c, not 1.8 c. The second rocket moves at about 99.4% the speed of light relative to the ground, still less than c. You can keep stacking rockets inside rockets, each accelerating relative to the one before, and you'll never exceed c. The velocity addition formula prevents it. This is the second big misconception. People think you can keep accelerating indefinitely. That speed can increase without bound. But c is a barrier. It's not a speed limit in the sense of a law you could break if you tried hard enough. It's a structural feature of spacetime. Nothing with mass can reach c. Nothing can exceed c. The universe doesn't allow it. Now here's something even stranger. From the perspective of a photon, if a photon could have a perspective, time doesn't pass. A photon emitted from a distant galaxy billions of years ago, from our perspective, has experienced zero elapsed time. The photon is emitted and absorbed in the same instant, from its own perspective, because at the speed of light, time dilation becomes infinite. Gamma approaches infinity as v approaches c, and length contraction also becomes infinite. From the photon's perspective, the distance between the galaxy and your eye is zero. The photon doesn't travel through space and time. It exists at a single point in its own reference frame. The concept of a journey doesn't apply. This is why we say photons are timeless. They don't age. They don't experience duration. Let me give you numbers to show how dramatic these effects are at high speeds. At everyday speeds, they're negligible. A car going 60 miles per hour, about 27 meters per second, has v over c approximately 9 times 10 to the power of minus 8. The Lorentz factor gamma approximately 1 plus 1/2 v over c squared approximately 1.00000000000000004. Time dilation and length contraction are 1 part in 10 to the 15th power, utterly unmeasurable. This is why Newton got away with absolute space and time. At low speeds, relativistic effects are invisible, but at high speeds, they dominate. At 0.1 c, gamma approximately 1.005, small but measurable. At 0.5 c, gamma approximately 1.15, noticeable. At 0.9 c, gamma approximately 2.3, huge. At 0.99 c, gamma approximately 7. At 0.999 c, gamma approximately 22. At 0.9999 c, gamma approximately 71. The closer you get to c, the more extreme the effects. Time slows down, lengths contract, mass increases, all without bound as v approaches c. Particle accelerators routinely accelerate particles to speeds above 0.999 c. The Large Hadron Collider accelerates protons to 0.9999991 c. At this speed, gamma is approximately 7,500. From the lab's perspective, the protons circle the 27-kilometer ring about 11,000 times per second. But from the proton's perspective, time is dilated by a factor of 7,500, and the ring is contracted to about 3.6 meters in circumference. To the proton, if it could perceive, it's going around a tiny loop. Both perspectives are valid. Both give correct predictions for what happens when protons collide. This brings up the third big misconception. People think relativistic effects are just high-speed curiosities, weird things that happen at extreme conditions but don't matter in everyday life. Wrong. Every time you use GPS, you're relying on relativistic corrections. GPS satellites orbit at about 14,000 kilometers altitude, moving at about 14,000 kilometers per hour. Two relativistic effects matter. First, Their speed causes their clocks to run slow by about 7 microseconds per day compared to ground clocks. Second, they're in a weaker gravitational field, which by general relativity causes their clocks to run fast by about 45 microseconds per day. The net effect is about 38 microseconds per day fast. If you didn't correct for this, GPS positions would drift by about 10 kilometers per day. GPS wouldn't work. Every phone, every navigation system, every precision-guided anything relies on Einstein being right about relativity. Or consider particle physics. When cosmic rays hit the upper atmosphere, they create muons, unstable particles with a half-life of 2.2 microseconds. These muons travel at about 0.98 c. In 2.2 microseconds at that speed, they should travel about 660 meters before decaying. But the atmosphere is about 10 kilometers thick. The muons shouldn't reach the ground, but they do. Why? Time dilation. From Earth's perspective, the muons' internal clocks are running slow by a factor of about 5. They live about 11 microseconds, long enough to travel the 10 kilometers and reach the ground. From the muons' perspective, they still live only 2.2 microseconds, but the atmosphere is length contracted to about 2 kilometers thick. They travel 2 kilometers in 2.2 microseconds at 0.98 c and reach the ground. Both perspectives give the same result. Muons reach the ground. Relativity is verified. Now let's talk about mass. Einstein's famous equation E equals mc squared is often misunderstood. People think it means mass can convert to energy, like in a nuclear bomb. That's part of it. But the deeper meaning is that mass is energy. They're the same thing. A hot object has more mass than a cold object because thermal energy has mass. A compressed spring has more mass than a relaxed spring because potential energy has mass. When a particle accelerates, its kinetic energy increases, which means its relativistic mass increases. The total energy of a moving particle is E equals gamma mc squared. As V approaches C, gamma approaches infinity, so E approaches infinity. This is why you can't accelerate a massive particle to C. It would require infinite energy. But there's a subtlety. Physicists distinguish between rest mass and relativistic mass. Rest mass, m0, is the mass measured in the object's rest frame. It's invariant. All observers agree on it. Relativistic mass, m equals gamma m0, increases with speed. It's not invariant. Different observers measure different values. Many modern physicists prefer to only use rest mass and say that energy increases with speed, not mass. But the concept of relativistic mass is useful for understanding why you can't reach C. The faster you go, the more energy is required to accelerate further, without bound as you approach C. Here's the fourth misconception. People think you need a force to keep something moving. This comes from everyday experience. You push a box, it moves. You stop pushing, it stops. But that's friction. In the absence of friction, in space, for example, no force is needed to maintain constant velocity. Newton's first law, an object in motion stays in motion unless acted upon by an external force. This is inertia. Speed doesn't require force. Acceleration does. Change in velocity requires force. But constant velocity, any constant velocity, requires zero force. A spacecraft coasting through interstellar space at 0.9 c experiences no force. It's not being pushed, it's just moving, and it will continue moving at 0.9 c forever unless something pushes on it. This connects back to relativity. If you're on that spacecraft coasting at 0.9 c, from your perspective, you're at rest, you're not moving. The rest of the universe is moving past you at 0.9 c in the opposite direction. There's no experiment you can do inside your spacecraft to determine whether you're moving or stationary. The laws of physics are the same in all inertial frames. This is what Einstein meant by relativity. Not that everything is relative, not that truth is subjective, but that the laws of physics don't depend on your state of motion. They're the same whether you're on Earth, on a coasting spacecraft, on a distant galaxy. The form of the equations doesn't change. What does change is your measurements of space and time. If you synchronize clocks with Earth and then accelerate to 0.9 c and cruise for a while, your clock and Earth's clock will disagree when you check them. You've experienced less elapsed time. This is real. It's been measured. In 1971, Huffell and Keating put atomic clocks on commercial airplanes, flew them around the world, and compared them to clocks that stayed on the ground. The flying clocks lost about 60 nanoseconds compared to the ground clocks, exactly as predicted by relativity. Time dilation is real, and length contraction is real. The fastest spacecraft humans have built, the Parker Solar Probe, reaches about 0.064%, the speed of light at its closest approach to the Sun. At that speed, it's contracted by about 1 part in 10 million, unmeasurable. But if we could build a spacecraft that reached 0.9 C, it would contract to less than half its rest length. The crew wouldn't notice anything strange inside the ship. Everything contracts together, including their bodies and rulers. But observers on Earth would see a squashed spacecraft zooming past. Here's the fifth and deepest misconception. People think space-time is a fixed stage on which events occur, a background, like a theater where actors perform. But space-time is not a background. It's a dynamical entity. It has structure. And that structure is determined by the distribution of matter and energy. This is general relativity, Einstein's theory of gravity. Mass and energy curve space-time. Objects move along geodesics, the straightest possible paths in curved space-time. We perceive this as gravity. Earth orbits the Sun not because the Sun pulls on Earth with a force, but because the Sun curves space-time around it, and Earth follows a geodesic in that curved space-time. Near a black hole, space-time curvature becomes extreme. Time slows down dramatically. At the event horizon, time stops from an outside perspective. Nothing can escape because all future-directed geodesics lead inward. The speed of light is still c locally, but globally, light can't outrun the infall. Space itself is falling into the black hole faster than c. That's how a black hole traps light. Not by pulling on it, but by being a region where space is falling inward so fast that even light can't escape. This is the avalanche. Galileo recognized that motion is relative. Newton formalized mechanics but assumed absolute space and time. Maxwell's equations predicted light speed but didn't specify a frame. Michelson and Morley showed light speed is constant. Einstein resolved the contradiction with special relativity, making space and time relative. Minkowski reformulated it as space-time geometry. Einstein extended it to general relativity, making space-time dynamical. From this came GPS, particle accelerators, gravitational wave detectors, black hole observations, all of modern cosmology. And at the heart of it is this: speed is not absolute. There's no privileged reference frame. You don't have a speed. You have speeds, plural, relative to different things. The only absolute speed is c, and it's not really a speed. It's the structure of causality, the rate at which cause and effect propagate through space-time. You can't exceed it. You can't reach it if you have mass, and it warps space and time around itself to stay constant for all observers. Not magic, not paradox, just geometry, just space-time obeying Einstein's equations. That's all it ever was. And somehow, that's more beautiful than if speed were simple.